So, like, if you break your arm, the X-ray tech basically hands you this clean, jagged white line.
Right, yeah, it's totally binary.
Exactly. It's broken or it's not. The doctor points to it, you get a cast, and you just move on. But in the world of geospatial analysis, it's like the X-ray machine itself is blurry.
Oh, absolutely.
And the patient is constantly moving around. And sometimes, the doctor isn't even sure if they're looking at an arm or a leg to begin with.
Yeah, it is the absolute definition of diagnostic muddy waters.
Oh, sure.
And honestly, if you are listening to this, you're probably navigating those exact waters right now. You are gearing up for the GISP certification exam.
Yeah, the big one.
Specifically, Section 205 of the Geospatial Court Technical Exam, which it focuses heavily on understanding terms and prepping for the actual realities of spatial data quality.
Well, welcome to this deep dive, everybody. Today, we are your personal guides through the total wilderness of Section 205.
We've got a lot to cover.
We really do. We've pulled together this dense, pretty heavily technical textbook excerpt on data validation and uncertainty, along with a really targeted study guide transcript from the YouTube channel GISP Study.
Both are fantastic resources.
Yeah, they are. And our mission today is basically to decode all the jargon, untangle error from uncertainty, and just arm you with the exact mechanics and concepts you need to pass this specific exam section.
Right. So we are going to break down the theories, the taxonomy of errors, the mathematical models, and of course, the visualization techniques.
Without putting you to sleep, hopefully.
Exactly. We'll do it by looking at how these concepts actually operate under the hood, not just by, reciting flashcards.
Okay, let's unpack this, because before you memorize a single term for the test, we kind of need to establish the baseline philosophy here.
Yeah, the foundational stuff.
Right. The sources make a massive, massive point of distinguishing between fixing a mistake and, well, just accepting the unknown. So let's start with the most basic hurdle, which is data validation.
So validation is fundamentally about ensuring your data set accurately represents the real-world phenomena it's actually meant to describe.
Right.
You're checking for consistency. For the exam, this means comparing your spatial data to what the literature calls ground observations or true values.
So you're basically asking, does my map actually match reality?
Exactly. And you're measuring that match against established accuracy standards. So keep an eye out on the test for acronyms representing these standards.
Oh, yeah, the alphabet soup.
Right. Things like ISO, the International Organization for Standardization, or FGDC, the Federal Geographic Data Committee.
And OGC too, right? The Open Geospatial Consortium.
Yes, OGC as well. Adhering to those, that is validation. But there is a very specific trap here that catches a whole lot of test takers.
All the model builder trap. I saw this in the notes, and it's so tricky because Esri's ArcGIS has a feature literally called model builder validation.
Yep. Yeah.
So if I'm taking a multiple choice test and I see the word validation, my brain might immediately jump to the software tool.
Which would be a huge mistake on the exam.
Right.
Model builder validation in ArcGIS, it merely checks if all the steps of your computational model have been incorporated correctly.
So it's just checking the gears of the machine.
Exactly. It asks, do the inputs connect to the outputs without a syntax error? It checks the mechanics of the software tool. It does absolutely nothing to validate if your underlying data reflects the real world.
Okay, so a perfectly running model can still just spit out total garbage if the data itself is garbage.
Precisely.
Okay, so validation is verifying reality, but then the textbook introduces this concept of the conjoint need between error-based modeling and uncertainty-based modeling. And honestly, error and uncertainty sound like synonyms to me. My map is wrong, it's just wrong, right?
In everyday conversation, sure, you use them interchangeably, but in GIS, they're entirely different paradigms.
How so?
Well, error-based modeling focuses on the measurable difference between your obtained value and the true value. The goal is active minimization. Think about, calibrating a GPS receiver to reduce a systematic bias, or maybe filtering out random noise from a sensor. You are finding a mistake, and you are fixing it.
Okay, so if I'm playing darts, error is my consistently bad aim, like throwing 2 inches to the left every single time.
Right.
I can measure that exact distance from the bullseye, and I can actually fix it by just adjusting my stance.
That's a great way to look at it. Uncertainty-based modeling, however, acknowledges an unavoidable reality, which is imprecision.
Stuff you can't fix.
Right, because even the most sophisticated measurements cannot provide complete information. So when you're reporting under an uncertainty model, you are actually forced to include a range.
Like a margin of error kind of thing.
Exactly. You report a length as 10.5 plus or minus zero point 0.2 centimeters.
Got it. So going back to the darts game, if error is my bad stance, then uncertainty is, I don't know, a sudden unpredictable gust of wind in the room.
Yes.
I can't calibrate away the wind. I can't fix it. I just have to factor it into my throw and accept that the dart won't land exactly where the math says it should.
And what's fascinating here is how the text frames this as a conjoint need. The hypothesis basically argues that accuracy is a property of the measuring system.
So my stance, the dart's aerodynamics, my technique.
Exactly. But uncertainty is a property of the measurement result. It's where that dart actually strikes the board while fighting the wind.
Oh, man. That makes total sense. So you
Yeah.
need both models simultaneously. You need error models to fix the system you control and uncertainty models to accept the reality of the environment that you don't control.
They do not compete at all. They are conjointly needed to responsibly model any measurement process.
Okay, so if the wind is just an inherent part of GIS, the exam is definitely going to test how we categorize it.
Oh, absolutely.
And the textbook lists 5 major types of uncertainty. But, instead of just listing them off like a boring table of contents, let's apply them.
I like that. Let's do it.
Imagine I'm working on this massive real-world project. Say I'm rezoning a historic waterfront district for a big new mixed-use commercial development. Where does the uncertainty actually creep in?
Well, it creeps in immediately at the spatial level. So your first category is positional uncertainty.
Okay.
This is raw geographic inaccuracy. So in your waterfront project, maybe your surveyor's GPS signal bounced off a tall historic building, which creates a multipath error.
Right, so the signal gets confused.
Exactly. So the point on your map says the property line is here, but on the physical ground, it is actually 5 meters closer to the water.
Okay, so the geometry is literally just in the wrong place. But let's say the geometry is perfect. The line is exactly where it should be. The next category in the book is attribute uncertainty.
Right.
So my spreadsheet data attached to that perfect polygon is flawed. Like maybe the database says a building has 50 residents, but it actually has 500.
Yeah, that is classic attribute uncertainty. The spatial boundary is perfectly correct, but the descriptive non-spatial data is inaccurate or maybe just ambiguous.
Gotcha.
And then you have to consider temporal uncertainty, which is heavily tested, by the way.
So time introducing doubt.
Yes. For your waterfront development, are you using sea level rise data that was collected back in, say, 2018 for project breaking ground in 2026?
Oh, wow. Yeah, the world changes a lot in 8 years.
Coastlines erode. Using outdated currency for a present-day model introduces massive temporal uncertainty.
Right. Okay, so that brings us to the fourth one, which is thematic uncertainty.
Yeah.
And the source defines this as ambiguity in classification.
Right.
So like labeling a land parcel strictly as commercial, when in reality it's mixed-use residential and retail.
Yeah.
But wait, I have to push back here a little bit.
Okay, go ahead.
Isn't thematic just a fancy word for an attribute error? Like, if I label a building wrong, isn't that just a mistake in my attribute table? Why does it get its own entire category?
That is a very sharp distinction to make, actually, and it brings us to a really critical concept from the YouTube study guide, which is semantic uncertainty. Because attribute uncertainty is often just a factual error, right? Typing 50 instead of 500. But thematic uncertainty is about the meaning of the categories themselves. Semantic uncertainty arises from discrepancies in how we actually define spatial phenomena.
The meaning. So like how we define what commercial actually is in the real world.
Exactly. The study guide makes a linguistic point for the exam, which is that semantics is the meaning of words, whereas syntax is the structure of a language.
Right.
We rarely struggle with syntax in GIS because the database rules are super rigid, but we struggle with semantics all the time. And semantic uncertainty is driven by 2 specific causes: ambiguity and vagueness.
See, to me, ambiguity and vagueness sound like the exact same thing. I mean, if a boundary is vague, isn't it also ambiguous?
They definitely overlap in casual conversation, but mathematically in GIS, they are distinct.
Okay, break that down for me.
Ambiguity happens when we use imperfect indicators for a phenomenon. So a direct indicator has a clear correspondence, like measuring temperature with a literal thermometer.
Simple enough.
But in GIS, we often rely on indirect or surrogate indicators.
Oh, I see. Like trying to map poverty levels using satellite imagery of nighttime city lights as a proxy.
Yeah.
You're just guessing that fewer lights means lower income, which is obviously a huge leap. It's a totally indirect link.
That is textbook ambiguity. Multiple distinct conditions could cause those lights to be off. Now, vagueness, on the other hand, is a lack of distinction between boundaries or objects.
Okay.
It is when the real world refuses to be boxed into a category. So in your waterfront project, where exactly does the beach end and the coastal scrubland begin? There is no hard line drawn in the sand.
Right. This gradient, it fades from one to the other,
Exactly.
which feeds perfectly into the fifth and final type of uncertainty, modeling or predictive uncertainty. Because if my inputs are built on vague boundaries and ambiguous proxies, then the final predictive model, like, say, a flood risk simulation for this new development, is going to generate its own internal doubt.
It has to, yeah.
It might predict a flood zone, but only with, like, 65% confidence.
Exactly. The model compounds all the previous uncertainties.
Okay, so we have this incredibly messy waterfront data set. It's full of vague boundaries and proxy data. How do we actually measure and model this mathematically for the exam? Because Section 205 isn't just theory, right? It gets highly technical with the GISP toolkit.
It does get very technical. So let's start with how we handle vagueness mathematically. When you cannot assign a firm category to data, you use fuzzy logic.
Fuzzy logic. It sounds like an oxymoron. Like, how do you program a computer to be fuzzy?
Well, instead of discrete variables with hard lines where something is either a 0 or a 1, true or false, fuzzy logic converts semantic descriptions into spatial representations using a continuous scale of membership from 0 to 1.
Here's where it gets really interesting. Fuzzy logic is basically like describing a paint color as kind of teal instead of forcing it to be strictly 100% blue or 100% green.
I love that.
Yeah, so 0 means it's definitely not teal. 1 means it's absolute perfect teal. But a 0.6 membership means it's mostly teal with some blue creeping in. You're mathematically quantifying the kind of.
That is the perfect analogy. It enables the representation of complex phenomena, like your transitional coastal scrubland, that discrete variables just fail to capture completely.
And what about spatial boundaries? The source mentions epsilon bands. Are those sort of like the bumper lanes in bowling, but for true line segments?
Yes, exactly. Epsilon bands are mathematically defined areas around a line that have a high probability of containing the true line segment. So if your true boundary is the bowling alley lane, the epsilon band includes the gutters and the bumpers.
And if you're a city planner relying on that map, a wider bumper lane basically means you have no idea if that new water pipeline is going to safely bypass a fiber optic cable or just smash right into it.
Which is exactly why the exam rule is. Larger epsilon bands are directly associated with lower quality data. A wide band means high positional uncertainty.
Okay, that makes sense. So fuzzy logic and epsilon bands are great for acknowledging how messy the world is. But eventually, a decision maker is going to ask, is this map accurate or not?
They always do.
Right. So when we need hard validation, when we actually have to check our work against reality, what tools are we using? Because I know the basics, like ground truthing. Get your boots dirty in the field.
Sure, you already know ground truthing from your day job, but for the exam, you need to understand how it slots specifically into a broader validation strategy alongside things like topology validation and cross-data set comparison.
Okay, frame those up for me in an exam context. Like, what do I need to know?
Well, topology validation ensures spatial rules are upheld. So a classic ArcGIS exam scenario is using topology rules to detect slivers.
Slivers.
Yeah, those tiny, unintended gaps or overlaps between land parcel polygons that usually happen during digitizing.
Oh, shit.
Then cross-dataset comparison is taking your local municipal database and validating it against an independent, authoritative source like USPS address records to find discrepancies.
Just cross-checking.
Exactly. And finally, there is metadata review, which is proving your dataset complies with FGDC lineage and quality standards.
But how do we prove the accuracy statistically? The textbook heavily emphasizes the error matrix or the error table. And conceptually, I get that it checks accuracy, but how does the grid actually function?
Think of the error matrix as a grid evaluating categorical data. You place your dataset classifications, what your model predicted, on one axis, say the rows,
Okay.
and then you place the true values, what is actually on the ground, on the perpendicular axis, the columns.
So if I'm classifying land cover as either water, sand, or concrete,
You check each point. If your model predicted sand, and the ground truth is actually sand, that tally goes in the cell where the sand row and sand column intersect. And when you do this for every single category, all of your correct predictions form a diagonal line straight down the middle of the matrix.
oh wow. So the diagonal is my ultimate success rate.
Yes.
And any numbers sitting outside that diagonal in the other grid squares represent where my model got confused, like predicting sand where there was actually concrete.
Exactly. The off-diagonal tallies show you not just that you have an error, but what kind of thematic error your model is consistently making. It reveals the bias.
Okay, that makes the math so much more visual.
Yeah.
I like that. Now, there's one more modeling tool heavily emphasized in the YouTube source, the Monte Carlo simulation.
Yes.
Which, I mean, it sounds like a casino game.
It shares the casino's name because it relies entirely on probability and chance. A Monte Carlo simulation is used to predict the probability of outcomes when you have highly uncertain, random variables.
Explain the mechanism, like how does it actually work in a GIS environment?
Let's take your waterfront flood risk model. You have inputs with wide epsilon bands and fuzzy boundaries.
Right.
You don't just run the flood model once. You tell the computer to run the simulation thousands of times. For every single run, the software randomly tweaks the input variables just a tiny bit within their uncertainty ranges.
Oh, okay. So one run assumes the tide is slightly higher. The next run assumes the soil absorption is slightly lower.
Yes. And after 10,000 iterations, you look at the aggregate. If a specific city block floods in 9,500 of those simulations, you have a 95% probability of inundation.
That's wild.
The Monte Carlo method doesn't eliminate uncertainty, it quantifies it into a highly usable probability curve.
So what does this all mean? We've got the philosophy, the taxonomy, the epsilon bands, and the Monte Carlo simulations. But the textbook explicitly notes that responsible geospatial practice involves communication.
It really does.
If we just hand the mayor a definitive single-line flood map after running 10,000 messy simulations, we're essentially lying to them.
It is honestly worse than lying. It creates dangerous, unearned confidence. Decision makers look at maps and they just assume they represent absolute truth. Visualizing uncertainty is how we break that illusion responsibly.
We have to put the doubt directly onto the map itself.
Yes.
And the textbook gives a great breakdown of how to do this visually. Let's apply them to our coastal flood map. First up are error bars.
So error bars are graphical representations of uncertainty around a specific value. If you have a dashboard showing the estimated population in the evacuation zone, you don't just put 5,000.
Right.
You add an error bar showing it could be anywhere from 4,200 to 5,800.
Simple but effective. Next up are uncertainty surfaces, which the book says are often done with rasters.
This is where you create a heat map showing the spatial distribution of error. For example, if you are using a digital elevation model, a DEM, to predict where the water will flow, you overlay a raster surface that glows bright red in the areas where the vertical elevation data is known to be sketchy.
I love that. You can literally just point and say, don't trust the water flow prediction in this glowing red canyon.
Exactly.
Then we have transparency or opacity encoding.
This is very intuitive for the user. You vary the transparency levels of your map layers to indicate confidence. You get solid, bold colors where the data is highly accurate, and the map literally fades out, becoming fuzzy and transparent in areas with high vagueness or wide epsilon bands.
So the map dissolves where our confidence dissolves.
Exactly.
Similar to color gradients or hatch patterns, I guess. You might use a dark cross-hatched blue for a 95% flood risk and a very pale blue for a 30% risk.
Right.
And finally, the simplest method, pop-up text or labels.
Just providing explicit quantitative values. So when an emergency manager clicks on a neighborhood polygon, a pop-up directly states, evacuation route viability, 70% confidence level.
Man, if we connect this to the bigger picture, the overarching theme of Section 205 isn't just passing a math test. It's transparency.
Always.
Visualizing uncertainty minimizes risk. It ensures that stakeholders make informed choices, like whether to evacuate a hospital, rather than blindly trusting a flawed, overly confident spatial polygon.
It is the practical application of professional responsibility. You are exposing the limitations of your own data so others can operate safely within those limits.
Let's do a quick recap to lock this in for the exam. The textbook provided a sample question, which is absolute gold for anyone listening right now.
Oh, definitely.
It asks, which statement accurately describes the concept of data validation and uncertainty in GIS?
And the winning answer breaks it down perfectly.
Yeah.
Data validation involves checking the consistency and correctness of spatial data, ensuring it adheres to specified rules and standards.
So you are checking the system.
Yes. While uncertainty relates to the inherent variability and lack of perfect knowledge in spatial data due to factors like measurement errors, approximation, and model assumptions.
You are accepting the wind.
They are two sides of the same coin, both crucial for maintaining data quality.
You know, spending all this time in the weeds of epsilon bands and fuzzy logic, leaves me with a thought.
Let's hear it.
As GIS technology, GPS, and drone LiDAR become infinitely more precise, as our measurement instruments achieve millimeter accuracy, will our measurement uncertainty eventually just disappear?
That's a good question.
And if it does, will it only reveal that contextual uncertainty, like how messy, vague, and undefinable the real world actually is, was the real challenge all along?
This raises an important question about the future of our profession. We might perfect our tools only to realize the subject matter, the Earth, human behavior, ecosystems. It just refuses to be perfectly categorized.
Maybe the future of GIS isn't about perfectly mapping the world. Maybe it's about perfectly mapping our doubts about it, which brings us right back to that doctor's office. You want the X-ray to be a clean, binary white line.
But the real world operates in fuzzy logic. It operates in semantic ambiguity and epsilon bands.
And as a future GISP, your job isn't to pretend the X-ray is clear. Your job is to measure exactly how blurry it is, mathematically prove it, and communicate that blurriness so people can make safe decisions. Best of luck on Section 205 of your exam. You have the tools, you understand the mechanics, keep questioning, keep exploring, and we'll see you on the next deep dive.